Hi, welcome to the lecture series on analog electronics. This lecture series is a part of Let's Crack the Gate initiative by TEQIP Faculties. So, right now I am considering you as masters of small signal analysis. Today we are going to do problems related to that, only problems. Okay, let's start the first one. Here you have a circuit. We haven't analyzed the circuit. We haven't derived the equations for the parameters of this circuit. So this is something new. So we have to do all the work. We don't have any equations with us. Okay. So in this question, the voltage gain AV of the circuit shown below is what? So there is a circuit. You can see the biasing here, that is collector to base bias. So for this we have to find the value of AV. So for this question we are going to use RPi model. And before getting into RPi, the only thing we know about this transistor is beta is equal to 100. So we have to derive RPi first. From the DC conditions, we will derive RPi, and after that we can find out the voltage gain using the AC analysis. So the first step is DC analysis. So the circuit will become like this. This is DC analysis. We have a resistance here. Capacitors are open, so no need to consider them, and emitter is connected to the ground. Here we have VCC, which is 13.7 volts. This resistance is 12 kilo ohm, and this resistance is 100 kilo ohm. Now the current in this resistance is IC plus IB, and the current in this one is IB, and we have a voltage drop here which is VBE. Right, we know how to find the values of these currents and voltages. We also have beta equal to 100 in the question. Now you can try to find out the values of IB, IC or whatever you need, and pause the video here, do that, then come back. So we can write the KVL. So we can write the KVL for this loop. Let me show the loop. It's this one. So it will look like this. 13.7 minus 0.7, because this is a silicon transistor. As I have already told you, if there is nothing given about the transistor, it is always a silicon transistor. So 13.7 minus VB in the active region is 0.7. So that will be equal to, in 12K we have IC plus IB into 12K, which is the drop, plus in this resistance we have IB, so the drop is IB into 100K. Now we know that 13.7 minus 0.7 is 13. IC can be written as beta IB, so this becomes IC plus IB becomes beta plus 1 into IB into 12K plus IB into 100K. Now beta is 100, so beta plus 1 into IB into 12K becomes 101 into 12K, and we can take IB out and find out IB. So IB will be given by 13 divided by 101 into 12K plus 100K, and this will give us the value of IB as 9.9 microampere. So we can approximate it to 10 microampere, so that the calculations are simple. So IB is equal to 10 microampere, and now we have the equation for IB, which is the DC current, base current in the circuit. Now we have the value of IB. as 10 microampere. Now we can go for the AC analysis. So we know how to draw the figure for this one. So we have R pi model here. So this is our R pi. We have a voltage controlled current source here, and this is GMVBE. So this is our base, this is our collector, and this is our emitter. Now if you look at the figure, we can see that emitter is directly connected to the ground. Now the DC voltage here is removed so that only AC is present in the circuit, right? So this point is grounded. Now this is grounded. That means this 12 kilo ohm is now between collector and ground. So between collector and ground, we have the 12 kilo ohm resistor. Then this 100 kilo ohm is between collector and base. So between these two, we have a 100 kilo ohm resistor. Now there is a source resistance 10K is connected to the base. Capacitors are short circuited, and here we have our source Vs. Okay, and across this we have our V in. We have been asked to find AV, and the AV here is nothing but the voltage gain of the system. So this is our input. So V out divided by Vs. We need to find V out divided by Vs. Since we have IB, we can find out R pi, and R pi is given by Vt divided by IB. Vt is 25 millivolt. We have already found out IB as 10 microampere. 10 microampere is 0.01 milliampere. Now that will give us 2.5 kilo ohms, right? So this is R pi. Next we need to find out, this is VBE. Now we need to find out GM. GM is given by beta divided by R pi. Now the value of GM will be, beta is 100, so 100 divided by R pi is 2.5 K, so 2.5 into 10 to the power 3. So this will give us 0.04, and the unit will be Siemens. So GM is 0.04 Siemens. Now I am slightly modifying this circuit because we know that emitter is connected to the ground. So I am connecting these 2 points to the ground so that we get a better understanding. So this is connected to ground. This is also connected to ground. Voltage across this R pi is VBE because emitter is the ground. So VBE and VB are same. Now this RS was 10K. Okay, now we have few nodes here. This is 1, this is 2, and this is the reference node. If we write the KCL at the output node, which is this one, we will get this is across this we have V out. So the current here is V out by 12K. So V out divided by 12K plus GMVBE plus the current going here, which will be V out minus VBE divided by 100K. V out minus VBE divided by 100K. This will be equal to 0. right? So we can take V out terms together. So this becomes V out into 1 by 12k plus 1 by 100k plus VBE terms together will make GM minus 1 by 100k equal to 0. If you do this calculation, it will give us 9.33 into 10 to the power minus 5 into V out plus, we know what is GM. GM is 0.04. 1 by 100k will become 1 into 10 to the power minus 5. So this term becomes VB into GM, we have already found out as 0.04, and this 1 by 100k will become 1 into 10 to the power minus 5. If you subtract that from 0.4, there is not going to be much change. So this becomes 0.04 into VB, and that is equal to 0. Now we can write the KCL at the input node. KCL at the input node, that is here. Here we can see that the current here is VBE divided by R pi plus here it is VBE minus Vs divided by 10k minus Vs divided by 10k, and here the current is VBE minus V out divided by 100k, that will be equal to 0. That is all the currents. Now there are VBE terms. So VBE into 1 by R pi plus 1 by 10k plus 1 by 100k minus Vs divided by 10k minus V out divided by 100k equal to 0, right? So we know the values of all the resistances. We know R pi as 2.5k and we have all these values. So if we reduce this equation, that becomes VBE into 51 into 10 to the power minus 5 minus, I am taking Vs by 10k on the right side. So here we have V out by 100k, that becomes 10 to the power minus 5 into V out equal to 10 to the power minus 4 into Vs, 10 to the power minus 4 into Vs. Now we can multiply both sides by 10 to the power 5. So this becomes 51 VBE minus V out equal to 10 Vs. Let's say this is our equation number 1 and this is our equation number 2. So in equation number 2, substitute equation number 1. So from 1 we have VBE equal to minus 9.33 into 10 to the power minus 5 into V out divided by 0.04, right? So in this equation we can write 51 into minus 9.33 into 10 to the power minus 5 into V out divided by 0.04 minus V out equal to 10 into Vs. Now we can reduce this. This will give us minus 0.12 V out and this is minus V out is equal to 10 times Vs. So this is minus 1.12 V out is equal to 10 Vs. What we need to find is AV, which is equal to V out by Vs, that we can find from this equation as 10 divided by minus 1.12, which will be minus 8.9. Okay. So the magnitude of AV is given by 8.9. This is our answer. It was simple, right? Now this is a previous year GATE question. You see, this is how much you have to do for this question. But when you practice this, this becomes easier and easier. Anyway, this is easy, right? You just need to remember how to draw the equivalent circuit, and the rest of the things you know, how to apply KVL and all. The only equations you should remember is R pi equal to Vt divided by Ib and Gm is equal to beta by R pi, and that's it. Shall we move on to the next question? Okay. So this is the question. The transconductance Gm of the transistor shown in figure is 10 millisiemens. The value of the input resistance Rin is. We have already done this kind of analysis. So you need to find out Rin. We have already done the analysis of this particular configuration using R pi model. Since Gm and beta are given, we can find out the value of R pi. If we know R pi, we can draw the equivalent circuit for AC analysis. RC is not needed, so they haven't given any value for RC though. So that is one hint for you. Now beta is 50, GM is 10 millisiemens. So R pi is given by beta divided by GM. Beta is given as 50 and GM is given as 10 millisiemens, that is 10 into 10 to the power minus 3. So this will give us R pi as 5 kilo ohm. Okay. Now we can draw the R pi model of this circuit. So it will look like this. Here we have the R pi. Here we have GM VBE. And we don't need to consider RO because nothing is given about finding RO. At the collector we will have RC, and RC will be connected to the ground. There is no other resistor at the output. This is GMVBE. Now emitter in AC analysis will be directly connected to the ground because this capacitor is now short circuited. So emitter is directly connected to the ground. Now what is left? This 10K and this 10K. This end is connected to the base and this end is now ground. This end is also ground. So we can draw that here. There is a 10K here, another 10K here, and here we have our Vs. This is 10K, this is 10K, and this is R pi. Now what is Rin? Rin is the resistance when we look at the circuit from here, and we can see that Rin is up to this much because this is connected to the ground. So we can say that Rin is equal to 10K parallel 10K parallel R pi, and R pi is 5K. Now 10K parallel 10K is again 5K. So this becomes 5K parallel 5K. 5K parallel 5K is 2.5 kilo ohm. So Rin is equal to 2.5 kilo ohm. This was also a previous year question, but you can see that how simple it is, right? Now we can do the next problem. The next problem is this one. For the network of figure, determine Re, Zi, Zo, Av and Ai. Here beta is given as 140, Ro is given as 30 kilo ohm. Since Ro is given, Re is given, we are going to go for Re model. Here we have 3 kilo ohm as Rc. There are two resistors here, 68K and 120K, and that's it. That's all the resistance. In DC analysis, that is, if we want to find out Re, we have to do DC analysis first. In DC analysis, all the capacitors are open circuited, and in AC analysis, we know that all the capacitors will be short circuited. They are high enough so that they can be considered as short circuits. Okay. So let's do the DC analysis first to find out the value of RE. So if you do DC analysis, this capacitor is not present anymore, this is not present, this is not present. We have a loop here that looks like this. Now in this loop, IC plus IB flow here, and IB flows through this because the capacitor is open. So IB flows in these two resistors. So if you write the equation for this loop, that is, if you apply KVL in this loop, we will get 12 minus, here we will have VBE minus 0.7 is equal to IC plus IB into 3K plus IB into 120 plus 68K. Now we know that IC is beta IB. So here we will get beta plus 1 IB into 3K. So this becomes beta plus 1 to IB into 3K plus IB into 188K, right? So on the left hand side we have 11.3. So if we find out IB, IB will be equal to 11.3 divided by beta is 140, so this becomes 141 into this 3K is there, 3K plus 188K, and this will give us around 18.6 microampere. This is the value of IB. If we have IB, we can find out IE. IE is equal to beta plus 1 into IB, and beta is 140, so this is equal to 141 into IB, and IB is 18.6 microampere, so this is 18.6 microamps, and this will give us 2.62 milliampere. So this is the value of IE. If we have IE, we can find out RE, and RE is VT divided by IE, and VT is 25 millivolt, IE is 2.62 milliampere. Now this will give us 9.54 ohms. So RE is 9.54 ohms. Yesterday I had told you that it is better to go for RPi model than RE model in some of the cases. This is one of those cases. Okay. So if we want to find RPi from RE, we know that RPi is equal to beta times RE. So that will give us beta is 140 and RE is 9.54. So 140 into 9.54 ohms, and that is equal to 1.34 kilo ohms. So this is the value of RPi. So now we can go for the AC analysis. Now if you look at the circuits, the capacitors are short circuits and DC supplies are grounded, right? So we can do the AC analysis. First we can draw the RPi model. So if you look at this figure, you can see that this 68K has one point connected to collector and the other point connected to ground, and this 120K will have one point connected to base and the other point connected to ground. That means the 120K is now in the base circuit, that is the input loop, and 68K is in the output loop. Okay, so if I draw the circuit, it will look like this. We have no Vs, we have no Rs, so it is directly, we have R pi here and GM VBE or beta IB here, both are same. So beta IB here, then RO is given in the question, it is 30 kilo ohm. We can do a check here. That check is whether we should consider RO or not, and the check is, if RO is greater than or equal to 10 times RC, then we need not consider RO in the circuit. Okay, here we have RO equal to 30 kilo ohm, so 30 kilo ohm must be greater than or equal to 10 times RC. Now the value of RC is 3 kilo ohm, so we have this condition satisfied, that is the equality condition is satisfied, so that is enough. So we can write that no need of RO, we don't need to consider RO. So at the collector we have two resistance, one is this 3 kilo ohm and a parallel 68 kilo ohm. So we can draw it here, this is the 3 kilo ohm and this is the 68 kilo ohm, both are connected to the ground. This point which is emitter is also connected to the ground. This is R pi and this is beta IB. Here we have the V out. This part is the output side, and on the input side we have this 120K connected to the ground. So here we have just a 120K connected to the ground. Okay, so this is 120K, this is 3K and this is 68K. Here we have our input. So I can redraw this circuit. I can split it into two because this point is connected to ground and this point is connected to ground. So I will split that. This is connected to ground. This is also connected to ground. This is base and across here we have VBE. Okay. Now when you look from here, this is VI, this is II. So we have ZI here. This is V out and I out will be flowing like this. So here we have Z out. I think I should change this for better understanding. So let's put 68K here and 3K here. Okay, so I out is flowing here, and when we look from this side we have Z out. So we have already found RE, that was asked in the question. Next thing is ZI, next parameter. If you look at this figure, it is clear that ZI is 120K parallel R pi. So ZI is equal to 120K parallel R pi. That will give us, we have already found R pi as 1.34K. So this will give us 1.32 kilo ohms. Okay. Next thing is Z out. There is no need to consider R out. So Z out is also EC. If we equate II to 0, there is no IB. If there is no IB, there is no beta IB. So this doesn't, there is no need to consider this in the output. So Z out is equal to 3K parallel 68K. So this is 3K parallel 68K, and this is equal to 2.87K. So this is Z out. Next thing is, next parameter is AV. So AV is equal to V out divided by V in. Now V out can be written as minus I out into this resistance, which is 3K, right? If you look at the circuit, this one, we can see that a current flows here, which is minus V out divided by 68K. So the current entering this junction and the current leaving this junction must be same. Minus V out divided by 3K plus minus V out divided by 68K must be equal to beta IB. So minus V out divided by 3K plus minus V out divided by 68K must be equal to beta IB. That means minus V out into 1 by 3K plus 1 by 68K must be equal to beta IB. That is, V out is equal to minus beta IB into 1 divided by 1 by 3K plus 1 by 68K. This is actually the parallel combination of 3K and 68K, this one. So we can write minus beta IB into 3K parallel 68K. Okay, I am not calculating this, you will understand why. Then V in can be written as, V in is same as VBE, so that is IB into R pi. So V in is equal to IB into R pi. So V out divided by VI, which is our AV, is given by minus beta IB into 3K parallel 68K divided by IB into R pi. So that will give us minus beta into 3K parallel 68K divided by R pi. So this is the equation for the AV in this kind of circuits. That is, 3K is our RC and 68K is a feedback resistance. Let's call it RF2. So AV will be minus beta into RC parallel RF2 divided by R pi. Okay. So beta is 140. So this is minus 140 into 3K parallel 68K will be equal to 2.87K divided by R pi is equal to 1.34K. Now this will be equal to 299.85. There is a minus. So minus 299.85 is the value of AV, the voltage gain. Now the next parameter is current gain, AI. AI is equal to I out divided by II. Now II can be written as VI divided by the parallel combination of this resistance. So II is equal to VI divided by 120K parallel R pi. 120K parallel R pi. Now V out is equal to minus I out into 3K. So I out can be written as minus V out divided by 3K. So AI can be written as I out by II, which becomes minus V out divided by VI into 120K parallel R pi divided by 3K. Now V out by VI is AV, so this becomes minus AV into 120K parallel R pi divided by 3K. This is minus of minus 299.85 into 120K parallel R pi is 1.34K divided by 3K. If you do this, you will get the answer as 132. So this is the current gain. Now you know how to do the analysis of different circuits. The last configuration we did, this is also a particular biasing configuration. It is called a collector DC feedback configuration. We hadn't discussed how to do the analysis of this particular configuration, but we have done that here in this problem. So that means whatever circuit is thrown at you, you should be able to analyze it in AC analysis as well as DC analysis and be able to solve the problems. So with that, I am winding up the lecture here. We will meet with a new device in the next class. I will keep it a surprise. We'll see you tomorrow. So we'll discuss how that device is made, how to bias it, and how to analyze it for DC condition. Hopefully in the next class. So we will meet in the next class. Until then,